We're taking a look at the beginning of our coke handling project, which is where the coke is fed from the coke yard onto a grizzly system which covers our reclaim feeder. This grizzly that we're looking at is made out of 1-inch flat bar in a egg crate configuration with 9-inch by 9-inch squares, such that none of the large lumps greater than 9-inch will pass through into the reclaim hopper, so that our feeder located below will not become plugged. The reclaim hopper and grizzly operation will hold approximately 8 hours of inventory when heap full. The front end loader operator, which has, the front end loader, which has an 8-yard bucket, which represents about 5.3 tons per bucket full, dumps material onto this hopper and keeps it completely covered. The material is being fed from the coke yard grizzly. It drops down from the reclaim feeder into the reclaim feeder, which is what we see the excitation of by all of these springs. The reclaim feeder has an amplitude of about 5/16 to 3/8 of an inch stroke. It continues to vibrate, carrying all of the material then into the feed skirt of the coke to crusher conveyor. This coke to crusher conveyor normally travels at around 220 feet per minute. It will deliver 108 tons per hour as currently designed. It has the capability, by speeding up the conveyor, to produce double that capacity to around 220 tons. The reclaim feeder also will handle this increased rate by increasing its amplitude proportionately. Looking at the tail end of the conveyor, showing the tail pulley appropriately guarded to prevent any accidents by personnel. On the far side, which we can't see, is a zero speed switch, which tells us that the conveyor is running, or in the case of the conveyor being activated in the demand stage to run, but yet there's a broken belt or some other means stopping it, the zero speed switch will detect that and sound an alarm. Okay, what we're looking at here is the outside of the reclaim pit structure. We see in the foreground our ventilation blower, and in the background our emergency escape and or maintenance tunnel. This maintenance tunnel is used to remove all of the machinery from the reclaim pit on an as-need basis. We also have a ladder system whereby we can use this as an alternate means of escape if need be. Okay, we're panning on the coke to crusher conveyor system as we exit the end of the reclaim tunnel and enter into the first section of the tubular conveyor gallery. We progress up into the magnet tower, where our magnetic separator separates any large magnetic particles from the burden of coke on the belt. This device is an electromagnet which will pick up any tramp metal that happens to be embedded in the load of coal. The electromagnet travels at around 350 feet per minute, so that in any piece that it does pick up will move off of the area very quickly without getting wiped off of the belt by the surcharge of material on our conveyor. The belt on the magnet is an endless belt. It's cleated, and will move the material off at a very rapid rate. It discharges the material after it breaks the magnetic field. It will then fall into our tramp metal chute, dropping down into a hopper located below. The belt continues up into the tubular gallery, that runs to the crusher tower. The crusher tower contains a pre-crusher where the material that has been fed through the Grizzly, which has a 9-inch top size, is then reduced to 3/4 by 0 size. Trying to focus on is the emergency shutdown switches. There are a series of these located along all of our conveyors. They're all hooked up to an emergency pull cord that runs the complete length of the conveyor. So in the event that there's any problem with anyone getting caught in it, material spilling off of it or whatsoever, all we have to do is pull the cord, which disengages the switch. The red flag actually will then move into the horizontal position as the indicator that that is the switch that has been tripped. Another safety device that we have on our conveyors are the belt runout switches. If our belt, for some reason or other, fails to track properly and moves from one side to the other, we have these runout switches at both the tail end and the head end of the conveyors, so that when the belt touches them, it'll trip the switch and stop the belt in that position. What we hear here is coke going through the crusher unit. It sets up quite a racket when it's being heavily fed. We're actually feeding the mill in spurts at the moment, probably at the rate of around 150 tons per hour, which is a little bit over design, but since we're feeding intermittently, the mill can handle it. We're looking at the zero speed switch on the mill, which is one of the protective devices. Anytime the motor is running and the shaft is not, it will shut the mill down. On the back side of this chute, we also have a plug chute switch. It's nothing more than a tilt switch that's mounted in the system, where it is then transported in the coke to boiler conveyor up into the boiler structures, where it is individually fed to one of the 3 boiler silos over boilers 8, 9, and 10. We're panning again on the continuation of the coke to boiler conveyor. We see the tubular gallery extending up to the head house of that conveyor, which consists of the drive. In the foreground, we see the dust collector bag house that picks up all of the dust that's being generated in our coke transfer, cleansing it and discharging it back into our number 1 and number 2 coke conveyors, which are drag chain conveyors. Underneath the structure, we see some shooting arrangements so that we can divert the coke coming up the coke to boiler conveyor either into the number 1 coke conveyor, which feeds boiler 10, or the number 2 coke conveyor, which are feeding boilers 8 and 9. I'm standing alongside of drag chain conveyor number 1 at the moment. This feeds the coke then into a chute that drops the pre-crushed coke down into our silos. The conveyor is controlled by a hand-off automatic switch driven through a 15 horsepower motor and gear reducer, driving this drag chain conveyor at a very nice, even and slow speed. You can see the rotation of the end sprocket turning at the moment. We have inspection doors throughout these conveyors so that we can inspect what's going on. The conveyors are totally enclosed, so from an environmental point of view, they're ideally suited for this application in handling the fine coke. The conveyors are basically positive displacement machines, such that if the chute were to plug up with coke, there would be no place for the material to go that is being drugged down here, and it would either overload the machine and trip it out, or most probably would lift up this door at the end of the conveyor, which is basically nothing more than a safety valve, so that when this door trips up, the micro switch that senses the door movement would trip the conveyor off then, and that would act as our safety device.
Coke is stored in the coke bunker above the feeder. The coke falls onto the feeder when the coke valve is open. There is a Level Art 1000 detector which indicates when this pipe is clogged. The coke falls onto the feeder. This is a Merrick gravimetric feeder. Once on the belt, it is weighed. The coke drops off the end of the belt, where it free falls down into the pulverizer. There is another indicator here, which indicates when this pipe is clogged.
Okay, this is the line where the material enters the pulverizer. It comes directly from beneath the weigh belt feeder, drops down through the stainless steel pipe, and goes directly into the bottom of the grinding chamber.
At this time, we'll take a listen at the mill so we can hear it in operation. Sound of the gear reducer. And the sound of the 300 horsepower Siemens Alice motor. The mill is now at 21,500 pounds per hour, full out capacity.
Okay, this is the inside of our DF roller mill. We have an air seal, air supply coming in that supplies air to our rotary air seal. This air seal distributes air through this red flexible hose out to each journal. The purpose of this air seal is to keep an airlock on the journals to keep the dirt out. Also on this seal we have a automatic lubrication system. This lubrication swivel located inside this green hose comes down through this distribution block and comes out the distribution block through the conveyor of the green hose to the suspension shafts and also the main journal shafts. Okay, the air seal, this is where the air seal line comes down into the journal. What it does, it provides air pressure into this area right here, which keeps dirt and material away from the seal. Okay, here we have the location where the air supply, right here the air supply enters the air seal, and here we have the lubrication line which supplies lubrication to the inside of the pulverizer. Up here we have a thermocouple which measures temperature of the inside of the mill, and here's a secondary temperature probe that Shell Oil has provided for their controls. Okay, here we have our automatic lubrication system. This is a pneumatically operated pump. We get our air supply from the plant through a filter, pressure regulator, and a lubricator. This pressure regulator, pressure inside of it is regulated between 40 and 60 pounds pressure. When the system is activated from inside, it opens up the solenoid valve, which allows air into the pump. Once the pump cycles, the grease then exits through this flexible steel hose. As the grease travels down the line, we go through a regulator pressure gauge. This pressure gauge shows us the pounds of pressure on each cycle. In other words, each time the pump is activated, this needle will rise to that amount of pressure. As the light grease continues, it goes on through a strainer which strains out any impurities that might be in the line. It comes on around and goes into the primary distribution block. Now this distribution block is made up of several piston-operated sections. Each time this grease goes through here, each one of these pistons and each of these secondary blocks has to make a full cycle back and forth to complete one cycle. Well, right here we have a micro switch that has a plunger on it. Each time the grease goes through it, it must go all the way through the whole system, each one of these pistons functioning, before we'll activate a plunger in this micro switch. And this micro switch is set up for approximately 5 cycles every time the lubrication is called for from the computer. If one of these pistons does not make a full cycle, this micro switch will immediately let them know inside. It'll give them a lube fault signal. On the other side here, where the grease discharges this primary distribution block, we have another micro switch. What this switch does, it has a plunger that operates back and forth. This plunger is spring-loaded, and it takes a certain amount of pressure to push this plunger up. Now when the lubrication system has cycled, pressure will come through here, put tension on the spring, and it will work the plunger up, which will push this micro switch in and maintain contact on the switch. This contact has to be maintained for several seconds, otherwise we will get a broken line indicator inside on the computer display. Okay, this is our discharge chute. What this chute is for, it leads into the bottom of the grinding chamber, and any pyrites or any hard to grind obstacles that get inside the pulverizer can fall down through this chute and exit out the bottom of it. So periodically, this chute is open, as I will now do, to discharge these pyrites. Normally, as you can see some of the material coming out, normally they have a this is just a sample of material coming out. Now as the feed is ground up, the feed is lifted up by air into our classifier. The fine material passes on through, and the coarser products are knocked back down for regrinding. Once the material is fine enough, it leaves the classifier through that large 24-inch pipe that we'll call our product line. It comes on around the 90, down as you follow the line, on in to the exhauster. The exhauster conveys the material on up through the pneumatically controlled coke valves and on up into the diverter valves. Bingo.
The coke and air stream is split into two by this splitter. It's split into two streams, one on the right and one on the left. Each of these streams is again split into two, giving a total of 4 separate coke and air streams.
This is the burner elevation. We have 2 main burner levels. Upper main gun and the lower main gun is located at the bottom. In the center we have our pilot and our natural gas elevation. Natural gas comes in from the side. This is the elevation where the coke is blowing in. On the upper elevation, we can either fire pitch or fuel oil. The same on the lower elevation. This is the lower pitch gun or fuel oil gun. It's a main gun elevation. How many fuels do you have? Well, we basically can put, right now we have 4 fuels. We can burn pitch or fuel oil in the 2 main guns. In this elevation, we burn fuel oil as a pilot or natural gas. This is the
purpose of this movie now. We will place a blue filter across the lens, which will enable us to look directly into the furnace. Please open the door. What you are now looking at is a coke flame as depicted by the black sections that is interspersed between the pitch that is being burned on both top and bottom. This coke is being introduced at a rate of 22,000 pounds per hour by means of 4 burners located tangentially around this combustion engineering tangentially fired boiler. The coke has been ground to a fineness of 90% minus 200 mesh. The ash content measured at the baghouse is measured at 99% burnout with only 1% carbon. Please close the door.
The handheld terminal, you can use this terminal to adjust the mill parameters for instance, to adjust the fineness of the grind or the delta pressure that's in the mill. You can also use this device to monitor any of the parameters of the mill, including delta pressure, mill speed, and others.
Okay, to the right of it, would you explain those bar graphs?
These bar graphs show the most important of the mill parameters, including the airflow in the mill temperature, mill speed and amps, spinner speed, differential pressure, and the coke air fuel ratio. A diagram showing the present status of the mill. It shows the most important of the mill parameters, and it also graphically shows the mill and the various motors. For instance, this is the mill motor. It's running at 74 RPM. Delta pressure here is about 6 inches. This also shows the spinner motor, which is at 55 RPM presently, and the exhaust fan. Outlet temperature here is 200 degrees Fahrenheit. The inlet is 325 degrees. We are feeding coke at a rate of 13,400 pounds per hour at this time.
And how many amps?
We're drawing a little over 200 amps on the mill motor.
This is the graphics panel which we use to monitor the transfer of coke from the grizzly to into the silos in front of each boiler. The control, all you do is select what silo you want to transfer it in front of which boiler, hit the start system, and the PLC automatically starts it up and fills that silo. When the level gets high, it automatically runs out the system and empties the belts. All of the lights on the panel indicate the operation of the system. The red lights tell you whether something is running, and the green lights tells you when it stops. The white lights are alarm lights, which alarm when there's trouble, and that indicates what shuts you down or why.
Boiler 10 baghouse. This baghouse takes all of the flue gas that is produced by boiler number 10, passes it through the baghouse, where all of the solid particles are separated from the gases before they go up the boiler stack. The baghouse, has 8 modules. Each module contains about 440 bags. The boiler can operate, depending upon load, with as few as 6 modules in service, one being out of service for cleaning, the other being out of service for some maintenance. We also have the capability of bypassing the baghouse entirely so that we can operate with the baghouse out of service, where the flue gases then will be diverted directly through the ID fan and out the stack. There is a bypass valve in that ducting as well. Through the ID fan and out the stack. There is a bypass valve in that ducting as well. The baghouses